Hey everyone, so today we're going to talk about approximating a derivative and then also talk about an integral as net change. So two really important topics for application problems. So the first thing I want to talk about is remember that the slope of a secant line, which is also AROC, that's average rate of change if you forgot. So average rate of change is f of b minus f of a over b minus a. So really important one to remember there. Okay, and we're going to be using that to approximate derivatives. Okay, so remember secant lines, it's somewhere where we're pretty close, we're trying to get closer, and we're trying to get as close as possible to getting that slope of a tangent line. And that's the instantaneous rate of change, and that's that limit definition right there. So we can approximate a derivative, really important. We can approximate a derivative by using the slope of the secant line, aka average rate of change. Okay, this should say f prime of c, really important that you change that. So we can estimate or approximate a derivative at c by using two numbers that are around it. So if, this was 1 to 3 and c was 2, some number in between, we can use average rate of change to approximate our derivative. Okay, don't forget that derivative just means rate of change. Really, really important one that's going to come up a lot. And I actually want to skip down here. We're going to come back and talk about this in a second. But actually take this information right here. We're going to skip down to right here, letter A, 1A. So water is being pumped into a tank over a 12-hour period. The rate at which water is pumped at, this is R of T, the rate, at various times. Here are the results, and R of T is in gallons per hour. T is measured in hours. We want to estimate R prime of 7. So this is where that average rate of change is going to come in. Okay, R prime of 7, we're going to talk about the meaning of it in a second, but for now, let's just practice estimating here. So you'll notice for 7, well, 7's between 5 and 8, so we're going to use these two table values here. So R prime of 7 is approximately R of 8 minus R of 5 divided by 8 minus 5, that average rate of change between 8 and 5. And again, we don't have a table of derivatives, so this is just an approximation. That gives us 9.3 minus 8.8 over 3, which actually simplifies to 0.5 over 3, or 1/6, or if you want a calculator, 0.167. Okay, so that would be R prime of 7. Now, really what is tough in this unit, and when we have these in free response problems on the AP exam, is figuring out what the context of the problem is, and what does the derivative mean in that context. Okay, so if you scan back up here, it says g of t. We're just going to try a couple examples. We're not going to actually do any math right now in terms of calculating. We're just going to say what is the meaning and context of these derivatives. So let g of t represent, it's the number of gallons of water in a lake at time t, which is measured in days. What does g prime of 5 mean? And again, we keep in mind that g prime means the slope or the rate of change of g at t equals 5. So we want to just say that, but using the units given. So we know that g of t is in gallons, okay, time is in days. And when I write g prime of t, remember that we can write this as dg dt. And this is actually super useful here because now we can kind of use this to find our units. What are the units of the derivative going to be? Well, g is in gallons, and t is in days. So our units here for g prime is gallon per day, or gallons per day, excuse me. So g prime of 5 represents the rate of change in gallons per day of the number of gallons in the lake, not just at any time, but specifically at t equals 5 days. Okay, so let's read that again. So g prime of 5, that represents the rate of change, okay, that's the slope, right? So the rate of change, that derivative in gallons per day, we want to mention that unit, of the number of gallons. So how did the gallons change in the lake? That's really what we're looking at. You measure the gallons one day, you want to know how is it changing, Okay, is it increasing? Is it decreasing? We'll talk about that more today. So in the lake at specifically 5 days, and we get that 5 from G prime of 5. Okay, let's try one more here. It says, let S of t represent the position of a car measured in meters. Okay, so S is in meters if you want to write yourself a note. And from the starting line at time t is in seconds. So what does S prime of 2.1 mean? Well, S prime of t, in general, we could write as ds dt, change of S over change in t. And this is going to be the change in position over the change in time. And those of you who take physics, you might recognize this as velocity, or if you took physics. So S prime of 2.1, excuse me, so this is going to be S is measured in meters, and time is measured in seconds here. So meters per second, we've heard of that before. So S prime of 2.1 is the rate of change of the car measured, we want to mention the unit, so measured in meters per second at t equals 2.1 seconds. Okay, and as I mentioned, this is actually velocity, which we're going to talk about a lot more, that relationship between distance, position, velocity, and acceleration. So S prime of 2.1, that's the rate of change of the car. How fast is the car moving, measured in meters per second, specifically that instantaneous rate of change at 2.1. Okay, and once you're ready with that, let's go on to R prime of 7. So the same problem, back to this water being pumped into a tank. Okay, we figured out what R prime of 7 is, So what is R prime of 7? Well, it represents, in the context of this problem, okay, the rate of change of a rate. So this is a little bit strange, but notice that R of t is already in gallons per hour. So if we find R prime of t in general, aka dr dt, this would be gallons per hour, I'm getting that right from the table, over hour, which is gallons per hour squared. So you might recognize this as kind of like acceleration here, the rate of change of a rate. Okay, so the sentence is going to be a little bit strange. So let me write it here for you guys. So R prime of 7 represents the rate of change of, well, it represents the rate of change of the rate that water is being pumped into the tank at t equals 7 hours. Now, another way to think about this, and another way we're going to write it, so again, we wrote it's the rate of change of the rate, so how is the rate of water changing? Okay, that's entering the tank. We could also say that water, and this is important, water is being pumped at an increasing rate at t equals 7 hours in gallons per hour squared. Okay, so water's being pumped at an increasing rate. So not only is there a positive rate of water, it's increasing. Okay, so think if you're accelerating in your car. Yes, you're going forward, but you're going forward at a faster rate. Okay, so it's an increasing rate at t equals 7 in gallons per hour squared. And increasing, again, this is because R prime of 7 was positive. So we're going to talk more about that as we go. Okay, so that's derivative context, and the next thing I want to talk about is kind of how do integrals fit into this. So if you guys are ready to go to that next page. And now we're going to talk about, we already talked about fundamental theorem of calculus on yesterday's notes. So that is that main concept right here, that capital F is the antiderivative of little f, right? So integral of f of x dx is the same as capital F of x plus c. And that also means that capital F prime of x is equal to f of x, little f of x. Okay, so a couple really important things here that we want to write down. Okay, so this one, we just talked about it above. F of x is the rate of change of capital F of x. So we talked about that on that whole first page there. Now, this one, really important here. This is your fundamental theorem of calculus we talked about. Okay, and that's going to represent the net change of f of x from a to b. So this represents the net change of f of x. All right, so the net change. And so we're going to talk about this below here with a rabbit population and this download speed of a computer. So same thing as above. We're not going to actually calculate anything right now. We're actually just going to figure out what's the context. Okay, so let's look at these three down here. We're just going to mention what's going on here and what does this represent. So what does the integral of r of t dt? So it says let r of t represent the rate of growth of a rabbit population in rabbits per day. Okay, so r of t is in rabbits per day. What is the integral from t1 to t2, so 2 times r of t dt represent? Okay, well, very similarly, usually I start out something like this, and I just say, all right, well, the integral in general, okay, would represent, so r of t is in rabbits per day. Let's just do this casually here. And then dt, okay, dt, this is change in time. dt is in days. So rabbits per day times day. Well, these would just cancel, and I would end up with number of rabbits. So think of it this way, guys. It's the net change in the population of the rabbits. Okay, there was a rate of growth, rabbit population and rabbits per day. Well, if I'm talking about this integral of r of t, I'm talking about how much did the rabbit population change, okay, from t1 to t2, whatever those times are. So I'll write this down here. So t1 to t2, r of t dt. This represents the change, the net change in the rabbit population from T1 day, whatever that is, to T2 day. You know, usually it's like 1 to 4, but this is just kind of a different context here. So biggest things you need to mention, okay, it represents the change, that net change in the population, and this is in number of rabbits, right? A population, number of rabbits. Okay, and you need to mention the upper and lower limits. So upper and lower limits, or lower and upper, I said those backwards. All right, let's try one more. Okay, it says b of t is the download speed of a computer in bytes per second. Okay, so b of t dt would be bytes per second, and then dt is in seconds. So what does the integral from 0 to 10 b of t dt mean? Well, if seconds cancel out here, again, this means overall, it's almost like you kind of get rid of this per second or per hour or per day. We're taking away, we're going backwards one step here. We're saying, all right, in general, I'm just talking about the number of bytes from 0 to 10. Okay, so it's going to represent the change in the number of bytes. So bytes. Okay, let's try to write this down here correctly. So from 0 to 10, b of t dt, that represents the change in the download speed in number of bytes from t equals 0 seconds to t equals 10 seconds. Okay, so this integral represents the net change, the change in the download speed in number of bytes. That was what we figured out for units, right? Just like up here, it was population of rabbits, number of rabbits. And then we mention from 0 to 10. So if I took a measurement and I said, okay, how many bytes between 0 to 10 seconds? This would be the way to represent that, specifically this. Same with rabbits. All right, how many rabbits happened between these 2 days? Or not happened, how many rabbits were added to the population? Okay, added or subtracted to the population. That would be this integral of net change. All right, so I want you guys to actually try this one. Okay, it's actually that water being pumped into a tank again, but I want you to explain this. So I'm going to ask you on the video here to write me a sentence. What does the integral from 5 to 12 r of t mean in this context? So write a very similar sentence to something like this, but use these new units below. Okay, so I'll let you guys try that. All right, so now we're going to just try one problem. Okay, so hang with me here. I know these are tough. We're going to try one total problem here. Yes, it's a page, but at the same time, it all connects. All right, so you're filling up your swimming pool to start the summer season. I wish. It's cold right now. At 1 hour, your pool has 250 gallons of water, and the pool is being filled with water at a rate of W prime of t is 300 root t gallons per hour. Okay, so the first thing you want to do is find W prime of 4. W prime of 4. And since we're already given the derivative, we simply plug in 4, and we get 600. Okay, this is in gallons per hour. This is already a rate, right, because we're talking about that derivative here. And now we're just going to explain what does this mean in the context of the problem. Well, W prime of t is the rate at which the water is filling up. So if I look exactly at the 4th hour, right at t equals 4, the rate at which the water is going in is 600 gallons per hour. Okay, it's increasing by 600 gallons per hour. So let's write that down. At t equals 4 hours, the number of gallons of water in the pool, and I'm getting that right from here, gallons of water in the pool, I'm not making this up, right from the problem. Now we have to mention something important, is increasing, oops, if I could spell increasing right, by 600 gallons per hour. Okay, so we had to mention what time it's at. We had to mention the answer. We have to mention the units correctly. And also we definitely 1000% want to say increasing, okay? And the reason we want to say increasing is because W prime of 4 was positive, and we're implying this is that rate of change, okay? And you must mention increasing. Now, if you got negative 600 gallons per hour, that'd be like if you had the drain open and your pool was losing 600 gallons per hour. So it would be decreasing. So it's important to mention increasing versus decreasing. All right, so then what about W of 4? Well, W of 4, remember, if W prime of t is gallons per hour, then W of t would just be gallons. Remember, this is the derivative of W of t. Okay, so in general, if we're just looking at W of 4, we're not looking at the rate of change. We're just looking at, all right, well, W4 is at t equals 4, there's some amount of gallons of pool in the pool, right? So at t equals 4, I look in the pool and I'm like, cool, it has, 50 gallons. Okay, so W4 means that at t equals 4 hours, we have a certain number of gallons in the pool. All right, now these next two go hand in hand, and we're going to kind of just solve them together. So now we want to explain, and we're going to find this value here from 1 to 4, W prime of t. Well, we're going to use our fundamental theorem of calculus. So from 1 to 4, W prime of t dt is from 1 to 4. This would be 300. It's square root of t. You guys see this up here? Square root of t, so I'm going to write t to the 1/2 dt. That gives us, so 300 t to the 3/2 divided by 3/2, aka times 2/3. This gives us, what would that be? 200 t to the 3/2 from 1 to 4, right? So this is where that fundamental theorem of calculus is coming in. And this is actually part D right here is what we're doing. I think it will just make our sentence a little nicer. So let's finish this up here. We're going to plug in 200 times 4 to the 3/2, which is square root of 4 cubed, minus 200 times 1 to the 3/2. And we end up with 1600 minus 200, which is 1400. And again, what do we know here, guys? We know that the integral of W prime of t which is the integral of gallons per hour, dt, so times hour, would be gallons. So this is going to be in gallons. Now, we know an integral, okay, represents net change. So this is basically just saying, all right, I have 1,400 gallons. That was what was added to my pool between 1 and 4 hours. Okay, so if I sat outside, I looked at my pool, I sat there from the first, t equals 1 to t equals 4. In the end, my pool would have gained 1,400 gallons of water. Okay, so that's what we want to say in our sentence. The swimming pool adds, why is it adding? That's because this integral, right, this net change was greater than 0. So instead of subtracts, it adds, or instead of loses, 1,400 gallons of water from t equals 1 to t equals 4 hours. That's how much was gained in that time. Just like the change of the rabbit population, that's how many rabbits were gained during that time. This is how many gallons of water were added during that time. All right, so nice thing we already did this. 1,400 gallons, that's from right up here. Okay, and last but not least, we'll finish this up here. Sorry, I know this is a bit of a lengthy video. Okay, very last problem, find the number of gallons in the pool after 14 hours. Okay, so we want to find overall that net change. What happened? Well, I want you to go back and read the problem really quick. It said at 1 hour, your pool had 250 gallons of water. So we don't want to ignore that. Okay, so at 1 hour, there was 250 gallons. You could actually just write that as W of 1 is equal to 250. All right, now you got to be careful here. Okay, you also know the net change from 1 to 4, we just did this above, was 1,400 gallons. Again, if you want to write that down, that's net change from t equals 1 to 4 hours. So I want you guys to think, if I started out with 250 gallons and I added 1,400, it's as easy as that. We're going to do W of 1, what happened, between 0 and 1 hours, we had 250 gallons, not equals, I meant to say plus what happened from 1 to 4. And that's going to give us what happened from 0 to 4. So the initial, that's what this was, initial plus the net change from 1 to 4, 250 plus 1,400 gives us 1,650 gallons at t equals 4 hours. So we took into account now, well, the original was 250 gallons, and we added from the first hour to the fourth hour, t equals 1 to t equals 4, I added 1,400 more gallons. So overall, I look at my pool right at the fourth hour, and I have 1,650 gallons. All right, so that is it. Again, sorry, I know this one was a bit lengthy. I hope you guys are okay with that in the sense that these are tough problems. It is a lot of writing, and we still have to try a couple more of these. Please bring in any questions, and thank you so much for watching.